Hi, everyone. This is Hidenori from Neural Network Group on PhyLab Entity Research. And today I'm going to talk about natural science of artificial neural networks and present our recent effort to understand the learning dynamics of deep learning theoretically. So to begin, let me first talk about why, as a physicist, we are now interested in the question biological and artificial neural networks. And then we, in fact, believe that these two fields are emerging frontiers in physics. And if we look back the history of physics, we can see a pattern here where both industrial and technological revolutions drive the creation of new fields in physics. The examples are, for example, how the efforts to build an efficient steam engine has led to beautiful theories of thermodynamics, or how in the last century, people have invented many semiconductor engineering, in particular the transistor. And then at the same time, people have created a new field of physics, solid state physics, and then now we more broadly call it as condensed matter physics. And even the most fundamental subject of physics, like particle physics, again, has driven by the rapid developments of particle accelerators, building. These are all also a contribution from engineering side, and the famous theoretical physicists who have unfortunately just passed away, Steven Weinberg, said that go for the messes. That's where the action is, where he called for this attention for the quantitative experiments that are presenting new mysteries for theoretical physicists, and then so that we can all work together. And based on these historical backgrounds, again, coming back to the brain science and machine learning, in brains, now we are increasingly being able to record from hundreds to thousands of neurons, and then we can also start to stimulate them externally. And then people also creating a maps of, again, many numbers of neurons and how they are connected through synaptic connections. In the side of artificial neural networks, deep learning has been taking off, enabling the machine to compete against human being in playing Go or classifying real world images and built in our social infrastructure. And then again, here from a scientific perspective, we can of course plot these activity of artificial neuron and then keep track of the artificial synapses through the entire course of learning, presenting great mysteries for physicists to work on. And given the time constraints, I can't explain all the kind of research that we do in our neural network group, but just to give you a snippet, we work on problems in biology, and then this is in fact actually a project from the days when I was a postdoc with my advisor, Surya Ganguly. And here we have asked the question of, can we derive experimentally testable hypotheses from artificial neural network models of the brain? And then we have constructed theoretical methods to model reduction to extract hypotheses from deep learning models. And over here at NTT, we've been working with intern Ekdeep, who has led amazing work asking the question of what are the state variables that indicates a success failure of normalization layers. And here, the final goal is to find like a variable such as temperature, entropy, et cetera, that can predict the performance of neural networks, indicates the performance of the neural networks in real world scenario. Okay. And today, I want to focus on this specific line of thought, focusing on understanding the mechanics of learning dynamics in neural networks. And you could see the references here. And I really want to highlight amazing collaborators, Daniel Kunin, Javier Sagastui-Brena, Daniel Yamins, and Surya Ganguly. And in particular, I want to highlight Daniel, who has collated all of these works together, and then who we share a lot of the thought process together for the contents that I'm going to present today. And these are all in collaboration with people from Stanford. So the opening question for this line of thought was that, what are the laws that govern the learning dynamics of artificial neural networks? And if you open up the black box of deep learning, what's happening when the deep learning models learn is that these millions of parameters are evolving over time upon the exposures to the new data so that the deep network can better adjust to the real world data sets. And then these time evolution of millions of parameters are governed both by the architecture of the deep learning model and then the optimizer. So the key question here is that researchers and practitioners spend a lot of time doing trial and error-based heuristic search. And then the question is, can we better understand the mechanism behind these time evolution of many number of parameters so that we can do engineering in a much more efficient way? And the key insight in building our theory for today's talk is to make a parallel between the dynamics of parameters during learning and the physical process. So learning dynamics happens in computers. So these are discrete updates of millions of parameters, as you could see here. But in making the analogy, the motion of an object in classical mechanics happens, of course, in continuous time and space. So the approach here is to build a continuous time models of learning dynamics by drawing elements from the classical mechanics. The first one is the equation of motion. Here we have this Newton's law, and the analogous question can be, is there any equation of motion or differential equation that can describe the learning dynamics accurately? And then after identifying the equation of motion, we care about symmetries in physical systems. And then an analogous question here can be, are there symmetries in the parameter space of deep learning systems? And then finally, in physics, we combine this equation of motion and symmetry to derive conservation laws, which puts a fundamental constraints on the time evolution of the physical system. And then what we derive by combining these two is application and extension of Noether theorem, so that these are generally applicable to any kind of learning systems. And this is a rubric that we want to follow today. And before going to the technical part of the talk, let me do some setup here. So there are 4 building blocks of the modern learning systems. The first one is a data set and task, where the data can be a pair of input image vector, where the pixel are represented by its vector elements. And then the output can be the category of an object like cat or dog. And the model gets this image vector inputs and then apply sequence of matrix multiplication by Q parameters and then nonlinear activations. And then to update the parameters, we need some measure of how good the model is doing on the task. And then that can, for example, be done by measuring the L2 error loss between the actual truth and then the model's prediction. And we finally update these parameters so that this error minimizes. So we do the steepest descent path on the error or energy landscape. And then that's what happens in the process of optimization. So let's start by identifying the equation of motion. So taking the most canonical learning rule, gradient descent, which is again, taking a descent path step by step, updating the parameters, we can think of it as forward Euler discretization of the gradient flow equation by taking the limit of eta. So eta is a time step size. And if you take a limit of eta going to 0, it's going to become a gradient flow. And let's compare that with a physical dynamics, Newton's equation of motion. And what you realize is that the Newton's equation of motion is a second order in time, while gradient flow is the first order in time. But in fact, if we incorporate the effect of finite learning rate to the first order, what we find is that the finite step size acts like a mass and introduce inertia to the learning dynamics. And as shown nicely in this animation made by Daniel, this red curve, the modified trajectory by modified gradient flow, pins through the black dots of discrete SGD updates, while the gradient flow original prediction deviates from that. Okay. And what's even nicer about this modified gradient flow framework is that now we can go to the Lagrangian formulation, and then the Lagrangian actually looks really similar to that what we are used to, where you have a potential energy here, which corresponds to the loss function. And then we also have kinetic energy, and this kinetic energy represents the learning rules or how you update the parameters. But in addition to that, another term that we always have in optimization is a dampening term, because in optimization, the goal is to go downhill and then converge at the minima and stop there. So you need to dissipate energy. And then that term is present here. And we can, of course, include more more elements to it by adding momentum, wave decay, building blocks of modern optimizers. And then we have set up theory in a really general way in the paper, but for here in today's talk, I want to use a gradient descent as a canonical simple example that we can explain in a simple terms. After identifying the symmetry of the potential function, let's now identify symmetry of the potential function of the loss function. And when we say symmetry, what we mean is that the function has a symmetry if it is invariant under a certain transformation, which is a large Q parameterized by S. And the examples are something that we can start from physics. So in physics, if we have potential energy, or in learning system, if we have loss function, we say a system has translation symmetry if you can move it in the parameter space in parallel, and then the loss doesn't change. And then this you can find in the softmax function of deep learning models. Similar analogy can be made for rotational symmetry. And then you can find it in the word embedding of modern deep learning systems. These two, translation and rotation, are common symmetries in physical systems, but in deep learning, the most popular symmetry is a scale symmetry, which is much less present in the physical system, which says that you can multiply the parameter vector by constant S, and then the loss function or the potential energy does not change. And this is present in the normalization layers in deep learning models and ReLU activation function. These two are present in almost every layer of modern neural networks, in particular computer vision scenario. So scale symmetry is everywhere. And after identifying the symmetry of the potential function, the next we want to move to the other term in the Lagrangian, which is a learning rule, or the kinetic energy, which is a velocity square. And then you can ask the same question: does the kinetic energy T have the same symmetry or not? And what we find is that for translation symmetry, as we kind of almost implicitly assume in physics, has the symmetry. The kinetic energy has a symmetry, and then you can shift the initial condition, and then you get exactly the same trajectory upon an equal amount of shift in space. As a result, the potential energy's time evolution is invariant under this translation operation. The same thing can be said for the rotation symmetry. You can get one trajectory rotated with a finite angle, and then you simulate it again, and then you just get a rotated trajectory with the same time evolution of the potential energy. However, for the case of scale symmetry, that's not the case. What you can find is that the scale symmetry, if you look at kinetic energy, the kinetic energy does not respect the scale symmetry of the loss function. And then this discrepancy of symmetry between the loss function and kinetic energy, unique, and then also everywhere in learning systems, creates some interesting dynamics, which is a motion of the previously conserved quantities. And this plot below is actually taken from a real world deep learning models training. And then you can actually shift the initial condition by scaling up the parameters. And then the loss function has that symmetry, but the learning dynamics is not symmetric. And then actually the performance of the model gets much worse. And again, key takeaway from this slide is that kinetic asymmetry, where the kinetic energy and the loss function has the same different symmetry. Motivated by this fact, we can not just take Nether's theorem, but also can apply it in a more creative way in the context of learning systems. And then that's what we have done. So this is a conservation law that we are really used to in physics, where you have a time-dependent conserved quantity. And then if in the case of translation symmetry, as we know it, we have a conservation of momentum in space. However, there is additional elements in learning systems. The first one is a damping. And just like physical systems, if you have a damping term, the momentum starts to exponentially decay, and the dynamics becomes absent in that direction. Furthermore, for the case of scale symmetry that are everywhere in deep learning systems, this kinetic asymmetry breaks the symmetry of the Lagrangian and induces a very interesting dynamics of the previously conserved Nether charge. And then that's what we're gonna focus for the later two applications. And then again, this theory can be also generalized for non-Euclidean type of dynamics, which I'm not gonna talk too much about today, but it can apply for that kind of scenario. And we can test this theory. And then for the case of scale symmetry, the previously conserved quantity was a time derivative of the norm of the parameters, and then we can keep track of them. So this is an original plot, which is a time versus parameters. And then you could look at the parameter norm in the middle plot as a function of time. And the prediction was a solution from the theory is on the right. And if you overlay them together, we can see how our theory matches with experiment exactly. And unlike many of the previous theories, we didn't need to make any big assumption here, except for the continuous time approximation. And this experiment basically suggests that our continuous time model is really matching the reality at the large scale. And let me finish by introducing two applications of our theory. The first application that we want to talk about is that we have identified the role of symmetry, explicit symmetry breaking in deep learning. And in deep learning, adjusting the effective learning rate is a really big issue. And then, as we just talked about, the parameter norm evolves in time due to the broken symmetry. And what we have found is that the spontaneous dynamics of broken symmetry induced learning dynamics, which is on the left, and totally independent, explicitly designed adaptive optimizers learning rate schedule exactly matches. And then these two equations might look messy, but the only thing that I want you to notice is that there are these three terms that are essentially playing the same role, but the key here is that on the left, it's not human design. On the right, it's really explicitly human design. And then the reason what we have identified is that the reason why the left thing has been working was it was tuned in a really spontaneous fashion. No one really designed it carefully, but it was built in that way. And our theory makes us three important predictions on the role of the finite learning rate, finite momentum, which is another element in the optimization of deep learning models, and the weight decay. And the question here is that do the dynamics of the broken NESA theorem basically helps optimization or not? And then what we find by ablating this motion of the NESA charge is that this degree of freedom, this NESA's learning dynamics indeed helps optimization. And then you can see that here. So the blue is ablation of the broken symmetry, and pink, if you let them be free, you can get the gain in performance. The y-axis is a test accuracy, so it's higher the better. Again, for the case of momentum, if you turn on the momentum factor, you can get a performance gain by the implicit role of NESA's learning dynamics, and the same holds for the weight decay as well. And another application of our theory was in the field of the pruning, which is to make neural networks much more parameter efficient. And here, the quick takeaway is that we were able to design a pruning algorithms that tries to conserve the pruning scores by taking the rescale symmetry of the ReLU function. And as a takeaway, our developed methods don't use data at all, but can go beyond the existing algorithms that can use data. And recently, this pruning algorithm has been finding applications in beyond pruning, but also in neural architecture search. To conclude, let me present a summary and take-home insights. The first insight is to look at learning dynamics as a physical dynamics. And then, even though we have been talking a lot about deep learning, these insights should also apply and hold for other optimization schemes like, and hopefully all the physical neural networks that physicists at Phylab are building. And then we have harnessed the symmetry of the Lagrangian. And the takeaway here is that unlike physical systems, the kinetic asymmetry is common in learning systems, and the geometry of the optimization methods and then the potential function or the loss function does not necessarily have to be the same. And this NESA's learning dynamics that we have derived accounts for dissipation, kinetic asymmetry, and non-Euclidean geometry that are inherent in learning systems. And then we have confirmed that this NESA's learning dynamics agrees experiments exactly in a quantitative fashion. And finally, our theory has also yielded a new insight on the role of symmetry breaking in deep learning, as well as led to an invention of a new pruning algorithm that can make neural networks more efficient. In the future, again, given the generality of our theory, it's going to be great to have more conversation with people at PhyLab and collaborators to see how these kind of view on the learning can be applied for broader class of neural networks beyond just deep learning. And I'd like to thank the collaborators again. And here is the end of my talk. Thank you very much.
Thank you, Hidenori. So the session is open for questions.
So you said the learning dynamics is sort of that of physical systems. And from that perspective, what is the expected role of the noise in the learning dynamics?
Yeah, so that's I can try to answer in the context of deep learning systems. And then like one thing I want to mention is lead author Daniel Kunin has an amazing paper on exactly focusing on the developments of the Langevin type dynamics and then asking the role of noise. But to answer to that question generally, so there are multiple beneficial roles of noise identified in the deep learning scenario. For example, the first one is in the deep learning system, the energy landscape is really winding in a sense that it's not really convex. And then there are many local pockets on the energy landscape. And the one way people have been trying to use noise, stochastic noise, is that to avoid subtle points of the local minima. So when the neural network got stuck in the local minima, then by injecting noise, you can try to get the network out of the local pocket so that you can find much better global solution. And another way people have been thinking about the stochastic noise is that in deep learning, you don't just want to optimize for the training data set. So there is a data set that you give when you train the model, but if you want to apply the network in real world, the network for the first time see new types of data. So there is always this issue of generalization to a newly observed data set. And then from that point of view, people have been, for example, hypothesizing that adding noise might guide the neural network to a wider solution in terms of the geometry of the optima of the energy landscape. So there are these sharp minima and wide minima, and then the hypothesis there is that adding noise will take you to a wide minima, which is much better for the generalization purposes. That's what I'm aware, in that context.
Hi, Hidenori. I had a question related to the algorithm used to train the neural networks, which is that stochastic gradient descent is usually the more naive one that people use. Often in practice, SGD with momentum or adaptive moments converges much faster. And I just bring this up because the initial algorithms that we use for running the neural network, for running the CIM, they're a lot like standard gradient descent. Do you think that gradient descent with momentum or these other more sophisticated algorithms would work better for CIM optimization too?
Let's see. That's a great question. And then I want to come back to one particular slide for that. So the takeaway from this slide basically was that in modern deep learning, you don't just have a stochastic gradient descent, but also the normalization layers. And then by combining these SGD and then the normalization layers, you get a learning dynamics that implicitly has these adaptive optimizations. So first, to begin from the deep learning point of view, my hypothesis there is that it might be that the normalization layers without unknowingly might be playing a role that the standard adaptive optimizer, the adaptive optimizer had been playing. So from the context of deep learning, one hypothesis is that adaptive optimizer might be less important given the presence of normalization layers. This has to be tested, but that's my one hypothesis. And then for training CIM or other physical network, there, I don't think so far people have come up with ways to implement normalization layers, which is crucial in deep learning, but I don't have any idea off the top of my head how to implement in a physical system. So there you might actually need to explicitly use adaptive optimizer to tune the learning rate to get similar type of learning dynamics. Yeah.
Okay, thank you.
So I have one question. So in your kind of Noether theorem-based kind of symmetry breaking and this analysis, you mainly focus on the parameter space.
Mm-hmm.
And so is there any efforts to use this kind of symmetry analysis to design the kind of physical connection between the nodes or the architecture of the neural network?
Mm-hmm. So one comment about that is that, when we talk about symmetry in deep learning systems, what is much more common is to think about symmetry in the data set, right? So, and then the concrete example is that, for example, if you have a cat in the image, the identity or the category, the fact that the cat is cat does not change even if it's a shift the cat location, right? So the label has this translation symmetry in the object position translation. And then people have been implementing that type of symmetry in the deep learning architecture in a way that the predicted category from the network does not change depending on the object location. And then that is how is actually the convolutional neural network has come up. And then this is again, much more mainstream kind of symmetry that people talk about in the field for the last, I'd say like 30, 40 years. And then more recently, people have been trying to implement symmetry that are much more unique to physics, like gauge symmetry, or with the application in mind to use these deep learning systems to analyze, for example, experimental data coming out from particle accelerators, et cetera, et cetera. So yeah, there is a separate effort trying to build symmetries from data into architecture.